All right, welcome everyone to the eCHT mini course given by Oliver Röndigs from Osnabrück, and he'll be talking today, Tuesday, again on Thursday this week, and then the following, and then a week from today, next Tuesday. So 3 parts, all about the motivic slice spectral sequence. Okay, go for it.
Okay, thanks a lot, Dan. Thank you for giving me the opportunity to give a talk in the seminar, or actually a mini course. So I'll try to be in some sense elementary in that I will give a couple of definitions regarding A1 homotopy theory, but I will try to move towards the slice spectral sequence fairly quickly. So this is my rough outline for today. And I would like to start with motivation coming from Algebraic Ktheory. So for every scheme X, Quillen defined a homotopy type, a space. So this here is not really a precise definition, but in some sense, you can sort of get the idea what is going on here. You look at the category of vector bundles over X. This is an exact category in the sense of Quillen. And then the categorical group completion can be performed, which gives you another category. You take its classifying space and the loop space of that. So this homotopy type is interesting, and its homotopy groups are the algebraic K groups of X. And if you prefer, you can think of X being an affine scheme, so spec of some commutative ring, and a vector bundle is then just a projective finitely generated module over R, and in particular the path components gives you back the Röndigs group K0. And let's specialize even more to the spectrum of a field. And then we know that every finitely generated projective module, even every projective module, is just free. So the Röndigs group is a group of integers. And we also know the first and the second K group. So this here is the group of units, K1. And K2, by a theorem of Matsumoto, is a quotient of the tensor product of the units with itself. And what you quotient out is the so-called Steinberg relation. So U tensor 1 minus U, where both U and 1 minus U are units in the field. And sort of there's the only fields where we know all the K-theory groups. These are the finite fields. It's a theorem of Quillen. Of course, there's more information known, but yeah, interrupt me if I'm wrong, but I think there is no infinite field for which all K groups are known explicitly. Yeah, and of course, topologists can proudly present their complex or real topological K-theory together with many spaces where all these topological K groups are known. And there are several reasons for that. One reason is that there's an Atiyah-Hirzebruch spectral sequence, which uses singular cohomology to compute topological K-theory. And yeah, assuming that algebraic K-theory is something interesting, one would like to proceed in a similar way. And this was expressed by Beilinson in a letter to Solé, 1982. I'm quoting here from that letter, where Beilinson expresses the hope that there is some analog of singular cohomology, which he calls motivic cohomology, and that there should also be an Atiyah-Hirzebruch spectral sequence similar to the topological situation, starting from motivic cohomology and converging to Quillen K-theory, at least for smooth schemes. So this is the motivation. And in order to work towards this sort of Bailen's hope or dream or whatever you might call it, it's worthwhile to look at some structural properties of K-theory. So here's one, in some sense, very basic theorem, the homotopy or A1 invariance. If X is a regular scheme and you look at the projection map from X times the affine line back to X, this induces an equivalence on the K-theory space. And in order to state the next structural property of K-theory, here's one definition. And the Sneevich square is a pullback square of schemes where one of the arrows is an open embedding and the other one going to X is an étale morphism. And there's an extra condition that the induced morphism on the respective complements on top and bottom of the square, that this is an isomorphism when you equip these closed subsets with the reduced closed subscheme structure. Yeah, so these are the Sneevich squares. As an example, if you can think of X being openly covered by U and Y, and the preimage being the intersection. And the other structural theorem due to Thomas and Trebon in the Röndigs Festschrift, if you have a Sneevich square of regular schemes, then the induced square on K-theory is a homotopy pullback square of spaces. And in particular induces a long exact sequence on homotopy groups. And of course, it's a bit unfair to state the theorem this way, because Thomason did a lot of work in order to be able to deal with fairly general schemes. And this theorem holds for quasi-compact and quasi-separated schemes, but you have to make sure that the K-theory space is actually not necessarily connective K-theory spectrum. Yeah, but let's maybe not worry too much about that. These are sort of the two structural properties, and this theorem of Thomson-Trebon, the so-called Sneevich descent for algebraic K-theory, is really one important motivation for looking at the Röndig topology generated by the Sneevich squares. So it was called the completely decomposed topology by Sneevich, and I'd like to give you sort of my favorite example of a Sneevich square, which is not a Zariski square. You take the field extension from the real to the complex numbers. If you like, take your favorite finite étale field extension, and this induces an morphism on affine lines over the respective fields. And then we take a closed point in the affine line over the reals, namely the one corresponding to the prime ideal t squared plus 1, where t is the parameter for the affine line. So this is a closed point. Residue field is the field of complex numbers. And when we use this to build a Sneevich square, the following happens. So let's take the affine complement of this closed point. This is an open embedding. Let's take this étale morphism F. And when we look at the preimage, then, well, the polynomial t squared plus 1 splits into two linear factors. So this gives us two closed points in the affine line. So the complement on the top consists of 2 points. The complement on the bottom consists of just 1 point. So the induced map cannot be an isomorphism. So this is not an Sneevich square, but we can massage it slightly and just remove 1 point in the affine line over C, for example, T minus I, and then you get an Nisnevich square. I shouldn't have called this my favorite example, because now you can say, oh, what a lame example my favorite example is, but well, that's what it is. Okay, so here's the list of properties that the Nisnevich topology has, and of course in this table I'm singling out the good part of the story. So I'm looking at the Zariski topology and the Étale topology. Nisnevich sits in between. And if, for example, we want that a smooth scheme locally looks like affine space, then this is false in the Zariski topology, true in the Étale topology, and also true in Nisnevich. And another property where the Zariski topology fails is the exactness of a flower star on the level of sheaves for finite morphisms. It's again okay for the Étale topology and Nisnevich, not true for Zariski. But of course the Étale topology has, well, the property that the cohomological dimension even of a field can be infinite. So I dub this third part here, fields are points. This is maybe a vague statement. Depending on how you interpret this, I mean, it refers to points of a topos. For the Étale topology, you have to pass to separable closures here. So that's one issue. And for example, the field of real numbers or the rational numbers, this has infinite Étale cohomological dimension, although it looks rather zero-dimensional from the point of view of Zariski and Nisnevich cohomology. Yeah, and the last property is the one I used as motivation. K-theory has Zariski descent. This is proven by Kenneth Brown, and also Nisnevich descent, but not Étale descent. Okay, so much for the motivation. And here's a very brief introduction to the Borel-Voevodsky motivic stable homotopy category for scheme S. Oh, I forgot to say, so I don't know what the current level of generality is, where you can define this. In the Borel-Voevodsky foundational paper, S was assumed to be Noetherian and of finite Krull dimension. Yeah, but the more general options exist. Okay, so the objects in this motivic stable homotopy category are called P1 spectra or motivic spectra, and these are Bausfield-Friedlander style spectra. So a spectrum, motivic spectrum, is a sequence of, let's say, some type of spaces, and these are connected by structure maps. The structure maps go from the P1 suspension of the nth level to the n+1st level, and every level is a space here over S, and this means it's a pointed simplicial presheaf on the category of smooth S-schemes. If you prefer, there are, of course, other variants. You can look at pointed simplicial, for example, Nisnevich sheaves. If you like, you can remove the simplicial direction, although this can be inconvenient sometimes. There are various options you have here. This is just one model, and sometimes the choice of model is inconvenient. Sometimes it is convenient. Okay, the maybe a bit awkward thing is that if we look now at a smooth S scheme, we can think of it as a representable presheaf, but this is then discrete. There is no simplicial direction, but that doesn't matter. And if you want to have it pointed, then it should have a rational point. Yeah, P1, for example, has several rational points. The most popular one being infinity, but up to A1 homotopy theory, as we will see, the choice of point does not matter. But of course, there could be schemes without any rational point. So unlike in topology, where you can point every space except for the empty space, this is a more subtle issue here. Okay. Let's then move on to the straightforward examples, the suspension spectra. Yeah, because of this issue with the base point, if we have a smooth scheme, let's just adjoin some disjoint base point. This thing called X plus. And let's take the P1 suspension spectrum, so iterated suspensions with P1. And take identities as structure maps, then this gives you the suspension spectrum of X. And in the special case where X is just the base scheme S, you get the motivic sphere spectrum over S. These are interesting spectra coming from the scheme direction. Of course, you can just take a pointed simplicial set and view it as a constant simplicial presheaf, and this also gives you a suspension spectrum. And for example, if you take the base scheme as itself pointed by the identity, this is a pointed smooth S scheme. This is the same as if you take the 1 point space and consider it as a presheaf. This is our zero object. Okay, and then this defines the objects. Here are, in some sense, this is the description of the morphisms. Yeah, more precisely, I'm saying rather unprecisely how to define the equivalences. They are forced by 3 conditions. The first one is the A1 invariance, so the projection from the product of smooth schemes and an affine line to the smooth scheme. This is supposed to be an equivalence. Then an Isnevich square is supposed to induce a homotopy push-out square of corresponding P1 spectra, suspension P1 spectra. This is the Isnevich descent, and then there's the stability with respect to the suspension with P1. Yeah, if you work this out in detail, you get the Morel-Wowarski motivic stable homotopy category. And I didn't mention this P1 stability explicitly in the context of Algebraic K-theory, but the first 2 were stated explicitly as properties of Algebraic K-theory, at least for regular schemes. So if S is regular, any smooth scheme over it is also regular. Okay, here are then some examples of spheres. So we have the usual topological or simplicial circle S1, delta 1 modulo its boundary, and suspension with it should be just denoted sigma. And here's another circle, the projective line. So the standard affine covering of the projective line, so you cover it with 2 affine lines, and the intersection of these affine lines is A1 minus 0. This is now a specific example of an Isnevich square, and by construction a homotopy push-out square. And since the affine line is by A1 invariance contractible, we get that P1 is the simplicial suspension of GM. And GM here is the affine line minus 0 pointed by 1, the multiplicative group. Okay, and here I have some notation for suspension with P1, which I might call the 1 plus brackets 1 sphere. That's the 1 plus brackets 1 suspension. And by P1 stability, now we get, in fact, spheres for every pair of integers. You should think of this S plus brackets W sphere as a sphere of weight W. Yeah, so the weight counts how many GMs we have, and then there's sort of a purely topological part. The little s counts how many S1s you have. I know there are way too many appearances of the letter S. My apologies. Okay, and if you look at, or if you're in the situation that, for example, you have a subfield of the complex numbers, then you can take complex points. And this, in fact, induces a nice functor. Here's an example which illustrates that the complex points of A1 minus 0, so this is the complex plane minus the point 0, this is, in fact, a sphere. Up to homotopy, it's the circle, S1. And this also happens if you have a subfield of the real numbers. The real line minus 0 is homotopy equivalent to a 0 sphere. So you can elaborate on these examples and get, for example, if you remove 0 from affine n space, then you get an n minus 1 plus brackets n sphere. And if you take the tome space of the rank n trivial bundle over the base, so affine space modulo the complement of 0. This is an n plus brackets n sphere. And by a fairly straightforward covering of projective space, this is also the same as collapsing an n-1 dimensional projective space in an n-dimensional projective space, the standard embedding. Okay. All right, if I'm too fast or too slow, I guess someone will raise his or her hand.
Well, let's pause for a second to take a break here and see if anyone has any particular questions they'd like to ask right now. Okay, let's just keep going, Oliver. Everything seems like it's going along smoothly, so just...
Okay. Thanks a lot. So here are some structural properties which are very convenient to have. There's a smash product on the motivic stable homotopy category. It's even a closed symmetric monoidal structure, and the unit is the motivic sphere spectrum, so the suspension spectrum of the base scheme with a disjoint base point attached. And it's also a triangulated category. The shift functor is just the suspension with respect to the topological circle, and homotopy co-fiber sequences define the distinguished triangles in this structure. And both the structures are nicely compatible. And there's a third part of structure. So what is straightforward to construct is when you have a morphism of base schemes from S to R. This defines a base change functor F upper star, basically because you can pull back a smooth S scheme X, a smooth R scheme X to S, and to get you a new smooth scheme. And this functor F upper star has good properties. For example, it's a strong symmetric monoidal. It's compatible with the equivalence with the triangulated structure, and it always has a right adjoint. Sometimes even a left adjoint. And I would prefer not to elaborate on this term six functor formalism, but there's plenty of literature. So in the context of the motivic stable homotopy category, the complete six functor formalism has first been documented by Joseph Ayub in his thesis. Let's see. Right, and here's some notation. Yeah, I don't know. I should have done this before. I should have apologized for my choice of bigrading. There are various choices you can make. This now is one that I think is convenient.
Yeah, the parentheses, the brackets around the W, that's new to me.
Yeah, so it's often you can see it as sort of pi s plus w times alpha, similar to the equivariance situation. The thing is that I will have plenty of alphas running around later, so I could imagine some different Greek letter instead of alpha, but I thought this notation fits well with the notation that is also used in motivic homology, where the round brackets around an integer tell you how many times you have to twist your given complex. Yeah, this is sort of the origin for this notation. So if you like, you can translate this as the probably more standard notation. This would be pi s plus w comma w. Yeah, but it's just notation. So I hope it's not, the notation is not too confusing. Yeah, then it's often convenient to consider all possible weights W at a time, and this is meant here with this direct sum. Okay. And sometimes it is also convenient to not just look at these homotopy groups or sort of graded homotopy groups, but in fact homotopy pre-sheaves or homotopy sheaves. So let's take a smooth S-scheme U, and then we can look at the morphisms from the S plus brackets W suspension of U with the disjoint base point to E. This is a pre-sheaf of abelian groups, and this can be sheafified with respect to the Nisnevich topology. And yeah, this sheafification is denoted with this underline, pi underline. And this is at least a bit related to the homotopy groups. For example, if you have a spectrum of a field, or more general, if S is local Henselian, then the global sections of this Nisnevich sheaf just give you back the homotopy groups as defined before. Okay. Right, and basically by construction, Röndigs was able to represent algebraic K-theory within the motivic stable homotopy category. So what I should have done is to insert some subscript S with this P1 spectrum KGL, but I didn't. And of course, there's also a reason for it. It's invariant under base change under F upper star. So let's choose a base scheme S, and let's think of equivalence K-theory presheaf on smooth S schemes. The previous notation was this calligraphic K. Yeah, one has to modify this only very slightly so that it's actually an honest presheaf. But then it fits the framework, gives you a pointed simplicial presheaf, and there's a certain structure map which corresponds to multiplication with the difference of a trivial and the tautological line bundle on P1. And yeah, if S is regular, we get a representation of equivalence algebraic K groups in this fashion. So the P plus brackets Q suspension of X plus mapping to KGL, this is the P minus Q equivalent K group of X. And if you want to know what happens if S is not regular, well, then you get Weibel's homotopy K theory. So the homotopy invariant approximation to algebraic K theory. Of course, it's more interesting to really look at the K groups itself, which are not A1 invariant for non-regular schemes, and there's lots of work going on in that direction, but I won't talk about that here. Okay, here's another example, and this is in some sense also straightforward to identify in this motivic stable homotopy category. You can look at, for every natural number n, the tautological vector bundle over the infinite Grassmannian of n-dimensional linear subspaces in some infinite dimensional affine space. This is also known as the classifying space of the nth general linear group. Yeah, and the Thom space of the tautological vector bundle you have there, this fits into a spectrum. Well, it would be nicer to express this as a spectrum with respect not to P1, but to the Thom space of the affine line. But that's only a slight change of coordinates in some sense. Okay, and just because this will come up later, there's a theory sort of theory of Chern classes or orientations, and this induces formal group law on this on the theory represented by this Thom spectrum, and it gives rise to homomorphism from the Lazare ring, so the polynomial ring over Z with countably many generators. And just so that it fits the grading, I would like to denote the degree of xk, or its image in the homotopy groups of NGL as k plus brackets k. And here's the in some sense fourth example of a spectrum. You might notice that I follow Wowodzki's ICM lecture in this context here. This is a really recommended reading as an introduction to motivic homotopy theory. Let's assume now that the base scheme is the spectrum of some field, and then there's a construction. I won't give any details now, but I'll give you a different definition later of an Eilenberg-MacLane spectrum for any abelian group of coefficients. And this motivic spectrum then represents the motivic homology theory that Beilinson was hoping for. So for example, for the abelian group of integers, this is integral motivic homology. And the connection with geometry, you can see in this second line here. Yeah, the first one is basically just a definition or notation of motivic homology. The second line tells you in the specific bidegree 2n, n, you get the nth degree n part of the Chow ring of X. So the part given by codimension n cycles. This is some classical object. And yeah, in general, you get Bloch's higher Chow groups with motivic homology. So this is a big theorem due to Suslin and Voevodsky that this motivic homology is in some sense the correct one. The connection with arithmetic, you can see here in the last line, the n, n motivic homology of a field with integer coefficients. This is Milnor Ktheory. And there's an index missing. It's the nth Milnor Ktheory. My apologies. And if you're interested in motivic homology over more general base schemes, there is a construction of a motivic Algebraic spectrum with good properties, such an E-infinity structure over any Dedekind ring, for example, over the integers. And this behaves well under base change, as Spitzweg proved. So if you like, you can think of some motivic Algebraic spectrum over any scheme. Okay. Let's now move to homotopy groups of motivic spheres, the stable ones here, of course, in this setting. I should, of course, mention that there's lots of interesting work on unstable homotopy groups of motivic spheres, for example, due to Aravind Azok and Kirsten Wickelgreen, Ben Williams, Jean Fazel. But if we want to look at the stable situation, then already several people have given partial answers. Of course, there's no complete computation, and we will be waiting for that for a very long time, I guess. And right, if I forgot your name and you're in the audience right now, then again, I have to apologize. Please let me know. Please raise your hand, and I'll do better next time. Okay, here's one, in some sense, rather straightforward property, but it's nevertheless very convenient. The motivic sphere spectrum is the unit in the symmetric monoidal motivic stable homotopy category. So this bigraded homotopy group admits a ring structure using that the smash product of spheres is again a sphere. And what you can also do is you can define a ring structure using composition of maps from spheres. And these ring structures are the same. And this is not just some ring structure. Well, as you might guess from this being a symmetric monoidal category, there's your commutativity property. So you have the twist automorphism on the multiplicative group, the commutativity isomorphism on the double smash product of the multiplicative group. And this induces an endomorphism on the motivic sphere spectrum. So this is in pi 0 plus brackets 0. And yeah, you can sort of guess if you want to move one element past the other element in this ring, then something has to happen with this commutativity isomorphism. And this here is the formula. The -1 is sort of what, of course, topologists and algebraists know when you deal with chain complexes. This probably no big surprise. And in some sense, also the epsilon should be no big surprise. It's just one further possibility to make mistakes in formulas with when you commute. So as a special case, if we fix some simplicial degree S and let the weight wander, then we get a graded module over this object here, pi 0 plus bracket star. And this holds for any motivic spectrum. So this sort of clarifies the universal role that the homotopic groups here play. We would like to understand this in some sense initial ring in this category. Okay, so you've seen one endomorphism of the sphere spectrum. Here are a couple more. The obvious ones. If you have a unit in the base scheme S, yeah, just think of some non-zero element in your base field, if it's a field. In any case, you can think of it as a morphism from S to A1 minus 0, and this then defines a map, which is usually denoted these brackets U, and this goes from the sphere spectrum to the round brackets 1 suspension of the sphere spectrum. And so here you get some minus 1 in the homotopic group. And the other, maybe less obvious map, but nevertheless very interesting map, is the algebraic Hopf map. So the affine plane minus 0 is a 1 plus brackets 2 sphere. It maps via the canonical map to the projective line, which is a 1 plus round brackets 1 sphere. So you get eta, which is in pi round brackets 1. These are the maps you can, in some sense, easily write down unstably and then also stably. And then one can play around a little. Maybe you would prefer to see a different definition of this Hopf map eta. And yes, what you can also do is you use the commutative group structure on the multiplicative group, and you can perform the Hopf construction on this group structure. And this gives you the same map. This is one lemma, which I recommend as an exercise if you haven't seen it. And thinking of these as some kind of generators, we can ask for relations. I don't know how obvious these actually are. So one relation, the first one is the Steinberg relation. This came up already in the second algebraic K group of a field. The idea that goes behind is as follows. If you take the product of the affine line minus 0 with itself, and you think of this sort of pair u comma 1 minus u as a map from the double pointed affine line, so you move 0 and 1 to this product of a1 minus 0 with itself. Yeah, when you pass to the smash product, this extends over the full affine line, so gives you the 0 element. This is a very rough and imprecise sketch of the argument for the Steinberg relation. And the two other properties you can easily get from the description of the Hopf map using the Hopf construction on the multiplicative group. So it's maybe not so easy to see via the canonical map from A2 minus 0 to P1, but it's easy to see using this equivalent definition using G. And the last relation is also rather straightforward once you express this element epsilon in terms of eta and these brackets -1. And then the hyperbolic plane relation is basically the fact that the multiplicative group is commutative. And what Morel and Hopkins did was to take these four relations and define Milnor-Witt K-theory for a field as the Z-graded associative ring given by these elements. There's now a sign shift in the degree so that it fits with other conventions. And yeah, these are the relations you have just seen. And one reason for the degree shift is that if you collapse the ideal generated by the element eta of degree -1, then you get something which is non-negatively graded, and a very old friend, this is Milnor K-theory. And yeah, Milnor K-theory maps to Quillen K-theory, and for a field, this map is an isomorphism in degrees 0, 1, and 2, and it stops being an isomorphism from degree 3 on. And there's now, thanks to the eta, a connection with quadratic forms. K0 is the Grothendieck-Witt of symmetric bilinear forms, and Kn for n-negative, Kn Milnor-Witt of a field is the Witt ring of symmetric bilinear forms. And there are some presentations of these two rings, sort of known presentations, which in some sense fit well with the description here. And then by design, you get this homomorphism from the Milnor-Witt K-theory to the zero line of homotopy groups of this motivic sphere spectrum. And Morel's theorem states that this is an isomorphism for any field. So what we get back is the identification of pi 0 plus 0 as the Grothendieck-Witt ring, and pi 0 plus brackets n, this is the Witt ring if n is positive. And so this is some partial answer to the question, what do we actually have as homotopy groups. So this is similar to the sort of the degree computation that pi 0 of the topological sphere spectrum is the group of integers. But as you see, these are sort of infinitely many groups together because we have this weight floating around. So one should, if one comes from topology, one should think of the Z2 equivariant situation. Okay. Next section, last section for today, is I'm going to introduce 3 filtrations on the motivic stable homotopy category. And these 3 filtrations will all be defined in the same fashion. Namely, I look at a full subcategory of the motivic stable homotopy category, which is closed under homotopy colimits and extensions. Yeah, so if I have a triangle, distinguished triangle, D to E to F, and D and F are in the subcategory, then also E. Okay, and Morel's homotopy T structure arises when you take the following generators. So you look at the Q plus brackets N suspension of suspension spectra of smooth S schemes. The Q is a fixed number and N varies through all the integers.
So Oliver, so this SH greater than or equal to Q, this is not closed under D suspension.
It is not closed
Right.
under simplicial desuspension.
Right. Okay.
It is closed under GM suspension and desuspension. So this is, yeah, when you compare with topology, this corresponds to the Q connective spectra. And this is then also, by lack of inventiveness, the notation here. The P1 spectrum in this full subcategory is then called Q connective. And if you want to know whether this can be measured by homotopy groups, well, one has to be a bit careful, but it can be measured using homotopy sheaves, at least if the base is a field. Yeah, this is this sort of the statement, or this is actually the definition that Morel used in order to construct this T structure. Yeah, I should say this is, I guess, due to Lurie. Whenever you have something closed under homotopy colimits and extensions, it's a degree 0 part of some T structure. Okay, and here are some examples. The sphere and MGL are connective, so with 0 connective, one just doesn't mention 0. Also, the Algebraic spectrum is connective, but Algebraic Ktheory is not. And this is, for example, visible from the fact that we have the 0th K group of a field coming up for every integer q when you look at pi q plus round brackets q. So, as Dan mentioned, this is not closed under simplicial desuspension, so it's not it doesn't give you triangulated subcategories, but the good properties are that it is an exhaustive T structure, and it's also Hausdorff. So if something is Q connective for every Q, it's actually the 0 object, the point. And the union of all these is the whole motivic stable homotopy category. That's so union in terms of colimits. Here's the second one. The first part looks almost the same, but now the roles are switched. We fix some weight Q, and then we let the simplicial degree float around through all the integers. So this is closed under simplicial suspension and desuspension, and turns out to be a triangulated, or I should say localizing subcategory. Yeah, these are the Q effective motivic spectra. And yeah, there's a canonical way to take the Qth effective part of a motivic spectrum. This is this functor FQ. This is the Qth effective cover. And I made a mistake here. I switched from F to S at some point, but not in every spot. My apologies. Yeah, so whenever you see F, you should think S. This works for any base scheme. No reason to restrict to a field. So here are some examples. The sphere spectrum, I mean, this is the suspension spectrum of S plus. So this is definitely 0 effective, so just effective. One can also check this for MGL, but KGL, this is not Q effective for any Q. And yeah, there's a natural homotopy co-fiber sequence from the Q plus first effective cover to the Qth effective cover. The canonical cone is the Q slice of E. So this now defines the name appearing in the title. And just to emphasize, It is triangulated. It is also exhaustive. Every motivic spectrum is the homotopy colimit of its Q effective covers, but it is not Hausdorff. And this is really a nuisance when it comes to convergence. We'll see this later. So here's an example. You look at this specific homotopy group, which turns out to consist of 1 and -1. So tau is -1 inside here. It gives you something in the mod 2 Allenberg-MacLane spectrum. If you invert this element, this happens to be Q effective for every Q. But it's not contractible. It represents étale cohomology with mod 2 coefficients. And in particular, it's not Q connective for any Q. So it's as bad as it can get. Yeah, for another example, if you invert eta, you get something which is connective but not Q effective for any Q. So this also happens. Yeah, as a structural result, the slice filtration behaves well with respect to multiplication. This appeared in Pablo Pelaya's thesis, and there's, yeah, in some sense, some slight improvement. Joint work with Javier Gutierrez, Marco Spitzweg, and Paula Östberg, which tells you that if you have a motivic ring spectrum, then the zeroth effective cover and also the zeroth slice are motivic ring spectrum. And there's a graded version. And in particular, since every motivic spectrum is a module over the motivic sphere spectrum, every slice is a module over the zero slice of the sphere spectrum. So the zero slice of a sphere spectrum will play a special role, and I'll say more on this very soon. Yeah, my time is closing into an end. Let me just give you a quick definition of the third filtration, because I said I'll give you 3 filtrations. This is the very effective slice filtration, which appeared in a paper with by Marco Spitzweg and Paula Östberg. So here you do not let one of these integers, either the simplicial one or the weight one, wander. This is going to be fixed. And by the same formal machinery, you get very effective covers, and also basically by definition, the sphere spectrum is very effective. MGL can be shown to be very effective, but this is not closed under simplicial desuspension. It is also not closed under GM desuspension. Yeah, so in some sense, you can see here the intersection of the 2 filtrations that I defined before. And the advantage of this filtration is that it is Hausdorff filtration, unlike the slice filtration. But the disadvantage is that it is not triangulated. So very effective slices will be harder to determine in general. We will see enough computations of usual slices then on Thursday, and these are rather straightforward. Yeah, just as an I'll repeat this here definitely on Thursday. This filtration leads to some spectral sequence. Let's not worry about that right now. Just to close this lecture, the slice spectral sequence for this motivic spectrum KGL, this is the motivic Atiyah-Hitzebruch spectral sequence that Bailenson wanted to see. So thank you. If you have any questions.
Okay, first of all, I'm going to unmute everyone so we can thank him, first of all. Okay, and I'm going to go ahead and mute people again to cut down on the background noise. We do have time for a few questions. Well, I have, and it's not exactly a question, more of a suggestion or a request, that next time at the beginning of the talk, can you review the 3 filtrations that you talked about kind of side by side in a kind of a compare and contrast kind of way? I mean, the indices are slightly different, and, you know, the sort of like the subcategories are slightly different in each case, and I'd like to
Yes.
just see the relationships very clearly.
Yes, I'll do so. That's
Okay.
that's a very good suggestion. Thank you.
Okay, great. Thanks. Okay. So with that, we will wrap it up here for today.